Hello guys, today we'll be looking at what we call probability, and this is a very realistic topic that has been integrated as much in our lives as possible. We use probability all the time. So for instance, we might be asked a simple question: are you going to school tomorrow? You might respond and say there's a 20% chance. That here is probability. There's a 40% chance that rain might fall tomorrow. That again is probability. There are so many different ways that we use probability. Whenever we flip a coin to decide to make a decision, that is probability. Whenever you roll a die to play a game, that is probability. All right. So probability is a likelihood or chance that an event will occur. All right, and we can see that in our daily lives. Now let us break down some important terms here. We talk about event. Now, what is an event? An event is the outcome of a random experiment. Why does it need to be random? To avoid bias. So there's a whole jargon of terms here that we must understand and we must know. But we use probability all the time. All right? Very essential part of our daily lives. Now, what we actually want to talk about today are the rules of probability. So to talk about the rules of probability, we need to establish some very foundation things here. And the first thing is what I call the sample space. So what is my sample space? The sample space is all the possible outcomes. All right? Simple example. When we roll a normal die, when you roll a normal die, and I'm going to call to represent the sample space, we use a capital S here. When I roll a normal die, this is what can happen. I can get a 1, 2, 3, 4, 5, or a 6. So this represents a set of all possible outcomes. Now, let us say we're interested in getting an even number. So let us call it A. So A is the event that we get an even number. Now, the probability of A is written as P of A. This means the probability of A. Now, of course, if I'm interested in getting an even number, I'm going to have to look at the number of even numbers I have, or the amount of items that I have in set A. Now, the even numbers here would be 2, 4, and 6. So what's the probability of getting an even number? We're looking at the number of even numbers that we have here. So the number of elements in A over the number of elements in the sample space. So the probability of A would be equal, how many elements do I have in set A? Here I have 3. How many elements do I have in the sample space? There I have 6. So the probability of getting an even number would actually boil down to a half, because half the numbers on a die are even, and this makes sense logically. Now let us look at a different event. Now let us say B is the event that we get a 7 when we roll a die. So let's go again. The probability of B would be equal to the number of elements in B over the number of elements in my sample space. Now B would be equal to an empty set because we don't have a 7 on an ordinary die. So the probability of B is equal to 0 over 6, which is equal to 0. All right. We call this event an impossible event. It cannot happen. And this is the lowest possible value that we can have. An event that is impossible, one that cannot happen. Because if we have faces labeled 1 to 6, it will be impossible for me to get a 7 when I roll a die. All right. Now, let us call a third event C. C is the event that we get a natural number. Now, let us look at an ordinary die. The numbers are 1, 2, 3, 4, 5, and 6. We're definitely going to get a natural number because all of these are natural numbers. All right. So the probability of C would be equal to the number of elements in C over the number of elements in the sample space. Now, what will C be? C will be equal to 1, 2, 3, 4, 5, 6. So my set C is actually equivalent to my sample space. So I could even go ahead and say the probability of C is equal to the probability of, well, the number of elements in my sample space over the number of elements in my sample space. So this would give me 6 out of 6, which is equal to 1. 1 is the probability of an event that is sure, an event that must happen. When I roll an ordinary die, I must get a natural number. It is a must. So the maximum value that the probability can have is 1, and 1 is the event that is very sure to occur, that must happen. We can now create a general rule. So if 0 is the lowest the probability can be, and 1 is the highest, we can start by saying that the probability of any event, let us call it the probability of A, must be in between 0 and 1 inclusive, where 0 is an impossible event and 1 is an event that is sure to occur. To establish most of the rules of probability, we can actually use a Venn diagram. Let us go back to event A. A is the event that we get an even number when we toss a die. So let us say that this is set A. I'm going to have my universal set, and of course this represents my sample space, and the number of elements in my sample space is equal to 6. Alright, now A is the event that we get an even number, and the even number on an ordinary die would be 2, 4, and 6. So what will actually not be in set A? It will be the odd numbers, which are 1, 3, and 5. So we all agreed that the probability that we get an even number is equal to 3 out of 6, which is equal to a half. Now let us look at the probability that we don't get an even number, and that is going to give me a complement. So first of all, we need to talk about the number of elements in my sample space minus the number of elements in set A. And of course, in order to get probability, we divide all this by the number of elements in my sample space. Alright, let us see what happens. The probability that event A does not occur. And by algebra, I can break this up and say the number of elements in my sample space over the number of elements in my sample space minus the number of elements in A over the number of elements in my sample space. And once I divide by that sample space, I am automatically going to get the probability. Now, when I divide the number of elements in my sample space over the amount of elements in my sample space, right, that breaks that down. So that is going to give me 1 minus the number of elements in A over the number of elements in the sample space will give me the probability of A. So here's our first rule. We can say that the probability that A does not occur, or that event A does not occur, is equal to 1 minus the probability that event A does occur. And we can manipulate this formula in several ways. We could say that the probability that event A does not occur plus the probability that event A occurs is equal to 1. Very critical in the line of probability here. To derive the other rules of probability, we're going to employ your knowledge of the Venn diagram. Looking at this question, it says that 50 students from a school entered for the CAPE exam. 10 entered for physics, 12 entered for chemistry, and 5 entered for both physics and chemistry. Alright. Now, we're going to use A, the students who entered for physics, and B as the students who entered for chemistry. So the first thing I want to establish on my Venn diagram is my universal set. We know that there are 50 persons who entered here. Alright, so let's break this down now. First we have physics, which is A, then we have chemistry, which is B. The first place you want to start in a Venn diagram is the intersection. And you do recall that there are 5 persons who entered for both physics and chemistry. Alright? We are told that 10 persons entered for physics, but that intersection will be included in that 10. So you have 5 in there already, which means you're going to have 5 out here. The persons who entered for physics, for chemistry, alright? So you have 5 in there already. It was 12 overall, so you're going to have 7 out here. Now, bear in mind that my universal set is 50. Now, when I add 5 and 5 and 7, all I'm getting is 17. So it means that there are 33 persons that are on the outside. Now, let us talk about the different sections of this Venn diagram. In A, we have 10 persons who do physics, but we have 5 that is in the intersection. So right here, we have A intersect B. The other 5 that we have in A is 5 only, those persons who do chemistry only. And there's a symbolic representation for that. It is A intersect B complement. Now let us interpret this from a probability sense. It is saying those who do physics and not chemistry. Alright? The intersection is those who do physics and chemistry. The 7 here is those who do chemistry only. So that is not physics and chemistry, which is B. And then here we have the outside. And this is a set of persons who do neither physics nor chemistry, and that is 33. So we're looking at A union B complement. But we say those who do not do chemistry or physics. Let us count to see how many persons do physics or chemistry. You have 5 plus 5 plus 7. That is 17. Now let us go back to the original numbers. Originally, we were told that there were 10 persons who entered for physics, and there were 12 persons who entered for chemistry. Now 10 plus 12 is actually equal to 22. So the question is, where did the extra 5 go? Now, because the intersection would have been counted in the number of persons who do physics, the intersection will also be counted in the number of persons who do chemistry. That means that the intersection was counted twice. Good. And right away here, realize that we can actually come up with a formula. So we are saying that the number of persons who do physics or chemistry would be equal to the number of persons who do physics plus the number of persons who do chemistry minus the number of persons who do physics and chemistry. Why? Because as we said, the intersection is counted twice, and so we have to subtract it once. Now, can I get probability out of this? Of course. All I need to include here is my sample space. So if I divide this by the amount of persons in my sample space, it means I would also do the same thing to the right hand side. So this works down to give me, I'm gonna put that in black, the probability of A or B. And of course, on the right hand side, I can break this up algebraically. So I have the number of elements in A, the number of persons who do physics, or the number of persons in the sample space, which is the number in the college who were entered for the exam, for the CAPE exam, plus the number of persons who do chemistry that entered over the number in the sample space again, minus the number who entered for both over the amount in my sample space. Good. So breaking this down, this now becomes the probability of A or B equal the probability of A plus the probability of B minus the probability of A and B. All right, let me highlight this. Now, this becomes one of our most important formulas, if not the most important formula. Right? So we're saying that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Very critical formula, a formula that you'll use very often in doing your questions. So ensure that you understand it and know it. You don't have to swat it because it comes directly from the Venn diagram.